June 13, 1944. Villers-Bas, France, 8:32 hours. The M4 Sherman never stood a chance. Captain Bradley watched through his periscope as the German 88 round punched through the lead tank's frontal armor like it was cardboard. The impact came from 800 yards, a flat trajectory shot that hit the glacis plate dead center. The steel didn't deflect the round. It didn't slow it. The projectile passed straight through 51 millimeters of rolled homogeneous armor, detonated the ammunition storage, and turned 4 men into statistics before they could scream. The second Sherman tried to reverse. The 88 found it anyway. Side armor, 38 millimeters. The round entered behind the driver's position and exited through the turret ring. The tank burned for 6 minutes before the crew stopped moving. Bradley's tank was third in line. Reverse, reverse now. His driver threw the transmission into gear, but the Sherman's weight and the narrow French road made retreat impossible. The German gun crew had already calculated the next shot. Then smoke rounds landed between them, artillery support buying precious seconds. Bradley's tank lurched backward into cover, engine screaming, transmission grinding. They made it behind a stone wall before the third 88 round cratered the road where they'd been sitting. 4 tanks had entered Villers-Bas that morning. 2 were burning hulks. 1 was disabled with a broken track. Bradley's was the only survivor. The problem wasn't courage, it wasn't tactics, it wasn't crew training. The problem was physics. American armor couldn't stop German guns, and men were dying because of it. Detroit Tank Arsenal, Michigan, July 1944. Thomas Garrett pushed his welding mask up and examined the seam he'd just completed. The bead was clean, penetration looked good, no spatter. 20 years working coal mines in Pennsylvania had taught him precision, underground. A bad weld on a support beam could kill a dozen men. The stakes here weren't different, just the scale. Around him, the arsenal floor roared with industrial noise. 300 welders working 3 shifts, assembling M4 Shermans at a rate of 12 tanks per day. Steel plates became hulls, hulls became fighting vehicles, vehicles rolled out to ships bound for Europe. The production line never stopped. But Garrett had been watching the casualty reports. He wasn't supposed to see them. Classified documents meant for engineering supervisors and Army liaison officers. But his station was near the quality control office, and papers left on desks overnight had a way of being visible to welders arriving for the 600 shift. The numbers told a story the propaganda posters didn't. American tanks were being destroyed at a 4-to-1 ratio against German armor. The M4's frontal armor, 51 millimeters at 56 degrees, couldn't stop the German 88 gun beyond 400 yards. Side armor was worse. Crews called the Sherman a Ronson after the cigarette lighter. Lights first time, every time. Garrett understood the problem in his bones. Steel was steel. You couldn't make it thicker without making the tank too heavy to move. You couldn't make it harder without making it brittle. The metallurgy had limits, and American tanks were already pushing them. But there was another variable nobody was adjusting: geometry. He'd seen it in the mines. When a roof support beam started to fail, you didn't just add more steel. You changed the angle of the load, distributed the force across multiple points, created spaces that let the pressure dissipate. A straight beam would snap. A braced beam with proper geometry would hold 10 times the weight. Armor worked the same way, or it should. Garrett walked to the prototype bay where damaged tanks were brought back for analysis. A Sherman sat on blocks, its frontal armor showing a clean penetration hole, 88 round, probably fired from 600 yards based on the angle. The projectile had hit square, transferred all its kinetic energy directly into the steel, and punched through like a nail through wood. He crouched beside the impact point, running his gloved hand around the entry wound. The metal had failed catastrophically, no deflection, no energy absorption, just straight-line penetration. But what if the round had hit something else first? Something angled, something that would force it to change trajectory before hitting the main armor. Garrett pulled a bent nail from his tool belt. He used them as makeshift scribes for marking cut lines. He held it against the tank's armor at a 45-degree angle, imagining the geometry. A projectile hitting that angled surface would have to change direction. The change would bleed energy. Even if it still penetrated, it would arrive at the main armor slower, weaker, off-axis. He stood, looking at the Sherman's flat, vertical hull. "You're thinking too loud, Garrett." He turned. Frank Chen, the night shift supervisor, stood with a clipboard and a tired expression. 58 years old, 26 years at Ford before the war, now managing 300 welders who thought they knew better than the engineers. "Just looking at the penetration, boss." Chen walked closer, examining the damage. 88 in close range. Crew didn't make it out. "They never do," Garrett pointed at the hole. "Steel can't stop it, not at this thickness." "So we make it thicker." "Make it thicker, tank gets too heavy, engine can't push it, transmission fails. Then you've got a 40-ton pillbox that can't maneuver." Garrett tapped the armor. "Problem isn't the steel, it's the geometry." Chen frowned. "Explain." "Projectile hits flat armor, all the energy goes straight through. But if it hits something angled first, something that makes it turn, makes it slow down, then the main armor has a better chance." "You mean sloped armor. The engineers already know about that. T-34 uses it." "Not just sloped, spaced." Garrett pulled out the bent nail, holding it a few inches in front of the hull. "Extra plate here, angled, welded to standoffs, creates an air gap. Round hits the outer plate, gets deflected or fragmented, loses energy crossing the gap, then hits the main armor weaker." Chen stared at the nail, then at the tank, then back at Garrett. "You're describing applique armor. The Army's been testing it for 6 months. Adds too much weight, interferes with mechanical components, costs too much to manufacture." "What if it didn't?" "Didn't what?" "Cost too much. Way too much." Garrett walked around the Sherman, gesturing at the flat vertical surfaces. "We're already cutting steel plate. We're already welding. What if we just added simple brackets and smaller plates, nothing fancy, just enough to create the geometry?" Chen's expression shifted from tired to interested. "Using scrap plate, standardized brackets, field installable." "Exactly." "The engineers will never approve it." "The engineers are designing perfect solutions that take 6 months to test and cost a fortune to implement." Garrett pointed at the casualty reports visible through the office window. "How many crews die while we wait for perfect?" Chen was quiet for a long moment. Around them, the arsenal floor hummed with the sound of 300 welders building tanks that would cross the Atlantic and face German guns with armor that couldn't protect them. "If you're wrong," Chen said quietly, "and we install something that adds weight without adding protection, we've made the tank worse, slower, easier to kill." "And if I'm right?" Chen looked at the penetration hole in the Sherman's armor, at the dried blood still visible on the interior surface, at the empty crew seats. "Build me a prototype," he said. "Off the books, night shift only. If it works, I'll take it to the engineers. If it doesn't, we forget this conversation happened." Garrett nodded. "I'll need scrap plate, 1/4-inch mild steel, and angle iron for standoffs." "Supply shed, keys in my office." Chen turned to leave, then stopped. "Garrett, you know this is your ass if it goes wrong, right? Mine too. I spent 20 years underground, boss. I'm used to betting my life on my work." Chen walked away. Garrett stood alone beside the damaged Sherman, holding a bent nail and thinking about geometry, about angles and air gaps, about the difference between armor that stopped rounds and armor that deflected them. Tomorrow night, he would start building. The question was whether anyone would let him finish. Detroit Tank Arsenal, July 18, 1944, 2200 hours. Garrett worked alone in the prototype bay, the overhead lights casting harsh shadows across the disassembled Sherman components. He'd requisitioned what the supply logs would call miscellaneous scrap steel, quarter-inch plate cut into rectangular sections, angle iron for mounting brackets, bolts that officially didn't exist in any inventory count. The design was simple because it had to be. Complex solutions required engineering approval, metallurgical testing, months of bureaucratic review. Simple solutions could be built in a night and tested by morning. He measured twice, marked the cut lines with his bent nail scribe, and fired up the cutting torch. The flame bit into steel, separating a 12 by 18-inch plate that would become the outer deflection panel. 4 of these would mount on the Sherman's frontal hull, spaced 8 inches from the main armor by angle iron standoffs welded at 45-degree angles. The physics were straightforward. An 88 armor-piercing round traveled at roughly 2,600 feet per second. When it hit flat armor, all that kinetic energy focused on a single point of impact. But if it hit an angled plate first, the round had to change direction, even slightly, and that directional change bled energy. Then it crossed an air gap where there was nothing to push against, losing more velocity. By the time it reached the main armor, it was slower, potentially fragmented, and hitting at an off-angle trajectory. Would it be enough? Garrett didn't know, but he knew doing nothing guaranteed men would keep dying. By 300 hours, he had 4 deflection panels cut and the standoff brackets fabricated. The welds were clean. 20 years of muscle memory made his hands steady even when his mind was racing. He test-fitted the first panel against the Sherman's glacis plate, adjusting the angle until it sat at precisely 43 degrees. That's not in the specifications. Garrett turned. Lieutenant Amos stood in the doorway, arms crossed, his uniform crisp despite the late hour. He was 26 years old, West Point engineering degree, assigned to the arsenal as a technical liaison between Army procurement and factory production. Smart enough to understand the work, young enough to care about regulations. It's a prototype, sir, testing a concept. Without authorization. With supervisor approval, Garrett gestured at the deflection panel. We're trying to solve the penetration problem. Amos walked closer, examining the angled plate and standoff brackets. His expression was unreadable, the careful neutrality of an officer deciding whether to report a violation or pretend he hadn't seen it. Explain the theory. Garrett walked him through it. The geometry, the energy dissipation, the historical precedent from mining operations where angled supports outlasted straight beams under equivalent loads. He kept his language technical but accessible, avoiding the condescension that enlisted men sometimes used when explaining practical knowledge to officers who'd learned from textbooks. Amos listened without interrupting. When Garrett finished, the lieutenant crouched beside the prototype panel, running his hand along the weld seams. The Army's been testing appliqué armor for 8 months, Amos said. Multiple configurations, different steel grades, various spacing geometries. None of them passed field trials. Too heavy, too expensive, or insufficient protection improvement to justify the weight penalty. How much weight did they add? 1,500 to 2,000 pounds per tank. Garrett pointed at his prototype. This adds maybe 300 pounds. Quarter-inch mild steel, minimal brackets, designed for field installation using equipment already in the tank. Mild steel won't stop an 88 round. It doesn't have to stop it, it just has to disrupt it. Garrett picked up the bent nail he used as a scribe. When I was underground, we didn't stop roof collapses with thicker beams. We changed how the weight distributed. Same principle. Amos studied the nail, then the armor panel, then Garrett. You're proposing we defend against the most advanced anti-tank gun in the German arsenal using quarter-inch plate and geometry. I'm proposing we test it. 1 tank, live fire range. If it fails, we learn why. If it works. If it works, You've solved a problem that actual engineers haven't managed to solve. Amos stood, which makes the engineers look incompetent and makes you look insubordinate for not following proper development channels. With respect, sir, proper channels are taking too long. Men are dying while we wait for perfect solutions. Amos was silent for a long moment. Outside, the night shift continued, welders assembling tanks according to specifications that everyone knew were inadequate. The production line moved forward because stopping it meant acknowledging that what they were building wasn't good enough. "I could shut this down right now," Amos said quietly. "Report the unauthorized modification, confiscate your materials, put a note in your file that would follow you for the rest of your career." Garrett met his eyes. "Yes, sir, you could. Or I could request a test firing tomorrow at the Aberdeen range. Completely official. Authorized ballistic evaluation of experimental armor configuration." Amos's expression didn't change. "But if the test fails, if this adds weight without adding protection, I'll make sure everyone knows whose idea it was." "Understood, sir." "Finish the installation. I want this tank ready for transport by 600. Amos walked toward the door, then paused. "Garrett, why are you doing this?" "Sir, you're a welder. Good pay, safe job, essential war work. You could keep your head down, follow the specifications, collect your paycheck. Why risk it?" Garrett looked at the Sherman with its scarred armor and empty crew seats. "Because I know what happens when the steel fails, sir. I've seen it underground, and I've seen the casualty reports from France." Amos nodded slowly. "Get it done." He left. Garrett stood alone with his prototype, the bent nail still in his hand, understanding that he'd just been given either an opportunity or enough rope to hang himself. He picked up the welding torch and got back to work. By dawn, the question would have an answer. Aberdeen Proving Ground, Maryland, July 19, 1944, 900 hours. The modified Sherman sat on the firing range, painted in standard olive drab, looking identical to every other M4 except for the 4 angled plates mounted on its frontal hull. The deflection panels caught morning light at odd angles, casting shadows that made the armor look layered, geometric, intentional. 50 yards behind the tank, a gallery of observers watched through reinforced glass. Lieutenant Amos, Frank Chen, 3 Army Ordnance engineers, and a civilian metallurgist from Chrysler. They'd been briefed on the modification but not its origin. Officially, this was a field innovation proposal undergoing evaluation. Garrett stood apart from the observers, helmet in hand, watching the range crew prepare the test weapon. A German 88mm anti-tank gun captured in North Africa, restored to firing condition, loaded with authentic ammunition. The same weapon that had been killing American tankers since 1942. Chen moved beside him. "You nervous?" "Terrified." "Good, means you understand what's at stake." Chen glanced at the observers. "If this works, they'll take credit. If it fails, you'll take blame. That's how it works." "I know. And you're still here." "Where else would I be?" The range officer's voice crackled over loudspeakers. "First test firing. Target, frontal glacis, center mass. Ammunition, 88 MPZ GR39 armor piercing. Range, 600 yards. Commence firing." The 88 roared. The round covered 600 yards in less than a second, a flat trajectory that gave the crew no warning, no time to maneuver. It struck the upper deflection panel at a slight downward angle, exactly where it would have hit the main armor on an unmodified Sherman. The impact sounded like a church bell struck with a sledgehammer. The deflection panel flexed, the angle forcing the round to change trajectory by 17 degrees. The projectile tumbled slightly, lost rotational stability, and continued toward the main armor, but slower, off-axis, fragmenting. When it hit the glacis plate, it penetrated 3 inches instead of punching clean through. Inside the tank, if there had been a crew, everyone would have survived. The observer gallery was silent. Garrett exhaled for what felt like the first time in minutes. The range officer continued. Second test firing. Target, frontal hull driver's position. Same ammunition, commence firing. The second shot hit lower, targeting the vertical hull section that was typically the weakest point on a Sherman. The deflection panel caught it, redirected it upward, and the round skipped off the main armor entirely, leaving a scar but no penetration. 2 shots, 2 survivable hits, against a weapon that had been killing Shermans reliably for 2 years. One of the engineers in the gallery stood abruptly and walked out. Chen smiled slightly. That's Hendricks, lead engineer on the applique armor project. He just watched a welder solve his problem with scrap steel and a bent nail. It's not about credit, Garrett said. No, but it's going to be about politics. The third test firing came without announcement, a surprise shot simulating combat conditions. The round struck the edge of one deflection panel, shearing off 2 mounting bolts but still deflecting enough to reduce penetration. The main armor held. Lieutenant Amos walked out of the gallery toward Garrett and Chen. His expression was carefully neutral. Fourth test, he said. Close range, 300 yards, then we're done. 300 yards was point blank for an 88. At that range, nothing was supposed to survive. The gun fired. The round hit dead center, maximum energy transfer. The deflection panel buckled, tore partially free from its mounts but held long enough to disrupt the projectile's trajectory. The main armor took the impact, penetration depth, 4 inches. Severe damage but not catastrophic, not unsurvivable. Amos turned to Garrett. You just saved that crew. The steel saved them, sir. The geometry saved them. Amos looked back at the tank. The steel just did what you told it to. The gallery emptied, engineers approaching the Sherman to examine the damage, measure penetration depths, photograph the deflection panels. Garrett watched them work, understanding that what happened next was beyond his control. He'd proven the concept. Now it belonged to the institution. Hendricks, the applique armor engineer, stopped beside him. 42 years old, MIT credentials, 8 months of failed tests behind him. Where'd you learn the geometry? No accusation in his voice, just genuine curiosity. Pennsylvania coal mines, 20 years underground. Hendricks stared at him. We've been approaching this as a materials problem, trying to find steel that could stop the rounds. You treated it as a geometry problem. Same thing happened underground. You can't always make the steel stronger, but you can change how the load hits it. I spent 8 months testing 12 different configurations. Hendricks's voice was quiet. $250,000 budget. None of them worked as well as this. You were testing perfect solutions, sir. This is just good enough to keep men alive. Hendricks nodded slowly, then walked back toward the damaged Sherman. Lieutenant Amos remained. There's going to be a report. I'll make sure your name's in it. Primary designer, field innovation, all of it. Respectfully, sir, I don't need my name in reports. I need this on tanks. It will be. I'm recommending immediate field trials in Europe. If those succeed, and they will, we'll retrofit the entire Sherman fleet. Amos extended his hand. You just changed armor doctrine, Garrett. They shook hands. But Garrett was already thinking about the production timeline, the logistics, the question of how fast they could get deflection panels onto tanks already in combat. Every day of delay meant more crews facing 88 guns with flat armor that couldn't protect them. The test was over. The real work was just beginning. And somewhere in France, men who didn't know his name were about to get a better chance at survival. Detroit Tank Arsenal, August 1944. The deflection panel design had been simplified for mass production. What Garrett had built as a prototype using scrap steel and improvised brackets was now a standardized kit. 4 panels per tank, pre-cut to specification, with bolt-on mounting hardware that installation crews could attach in under 3 hours. The Army had designated it Armor Supplemental M4 Series, bureaucratic language that reduced a coal miner's geometry insight to a part's requisition number. Garrett didn't care about the terminology. He cared about the production rate. Frank Chen stood in the logistics office, reviewing the manufacturing schedule with Garrett and Lieutenant Amos. Current output, 28 panel sets per day. That's 7 tanks. We've got 300 Shermans waiting for retrofit, and that number grows every time a new tank rolls off the line. Can we increase production? Amos asked. Not without pulling welders from primary assembly. We do that, overall tank production drops. Garrett studied the schedule. What if we don't install them here? Both men looked at him. Ship the panels as kits. Let the maintenance crews in Europe install them. They've got welders, they've got equipment, and they're closer to the problem. Chen frowned. Field installation means quality control issues. Different skill levels, improvised mounting solutions, potential structural failures under combat stress. We write clear instructions, include templates for positioning, torque specifications for bolts, weld inspection criteria. Garrett tapped the schedule. Right now we're bottlenecking at installation. If we shift that to the field, we can triple panel production and get protection onto tanks that are already in combat. Amos considered this. The Army doesn't like field modifications. Too many variables, too much risk of improper installation. The Army also doesn't like casualty rates. Garrett's voice stayed level. Sir, with respect, we can control quality perfectly here and watch men die while they wait, or we can trust trained maintenance crews to follow instructions and save lives faster. Silence. Chen picked up a pencil, running calculations on the margin of the production schedule. If we eliminate installation from our workflow, we could produce 75 panel sets per day. Maybe 90 if we add a third welding shift. That's nearly 400 tanks per month, Amos said. That's 400 crews with better odds of survival. Garrett met the lieutenant's eyes. Sir, we proved the concept works. Now we need to prove we can deploy it fast enough to matter. Amos stood, walking to the window overlooking the production floor. 300 welders building tanks that would cross the Atlantic and face German guns. The same cycle that had been running since 1942, except now there was a chance to change the equation. I'll recommend field installation protocols to Ordnance Command, he said. But Garrett, you're writing the technical manual. Every step, every specification, every inspection criterion. If a maintenance crew in France installs these panels wrong and a crew dies because of it, that's on you. Understood, sir. And you're going to Europe to train the first installation teams. 2 weeks, 4 forward maintenance depots, hands-on instruction. Garrett blinked. Sir, I'm a civilian contractor. Then we'll give you a temporary commission, Technical Sergeant, Ordnance Corps. You'll have rank, transport authorization, and access to forward areas. Amos turned from the window. You invented this. You need to teach others how to make it work. Chen smiled slightly. Congratulations, Garrett. You just got promoted and deployed. September 1944, Normandy, France, Forward Maintenance Depot. The maintenance base smelled like diesel fuel, welding flux, and mud. 12 M4 Sherman sat in various states of repair, crews working around the clock to keep the advancing Army supplied with functional armor. Garrett stood in front of 23 welders and mechanics, all of them exhausted, most of them skeptical. This is supplemental armor, he said, holding up one of the deflection panels. Quarter-inch steel, angled mounting, 8-inch spacing from main hull. It won't stop an 88 round. It'll disrupt it. A sergeant in the back raised his hand. We've been adding sandbags and spare track links to our tanks for months. How's this different? Sandbags add weight without changing geometry. Track links are too rigid. They transfer impact energy straight through. Garrett pulled out his bent nail scribe, holding it at an angle. This works because the angle forces the round to change direction. That directional change bleeds kinetic energy. It's physics, not luck. Prove it, someone said. Garrett had expected this. He gestured to Lieutenant Amos, who nodded to two MPs standing guard beside a captured German Panzerfaust, a shoulder-fired anti-tank weapon. They'd set up a test range 200 yards from the depot using a damaged Sherman hull fitted with the deflection panels. Watch, Garrett said. The Panzerfaust fired. The shaped charge hit the angled deflection panel, detonated, but the geometry disrupted the plasma jet before it could penetrate the main armor. The hull remained intact. The maintenance crews stopped talking. Garrett walked them through installation over the next 6 hours, positioning templates, torque specifications, weld inspection techniques. He emphasized the 43-degree angle, too steep, and the round would glance without energy dissipation. Too shallow and deflection would be insufficient. The geometry had to be exact. By evening, the first field-installed retrofit was complete. A Sherman that had arrived that morning with battle damage left that night with supplemental armor that might keep its next crew alive. Garrett moved between depots, training crews, troubleshooting installations, refining the field manual based on real-world feedback. He watched welders who'd never heard of him implement his design, watched crews who didn't know his name mount panels that embodied 20 years of underground geometry lessons. The system was spreading, not through engineering journals or technical conferences, but through maintenance depots and forward repair stations, welders teaching welders, crews sharing what worked. By October, 200 tanks in Europe had the supplemental armor. By November, 600. And the casualty reports were changing. December 1944, 3rd Army Headquarters, Luxembourg. General Patton stood in the intelligence briefing room, reviewing after-action reports from the Lorraine campaign. His chief of staff pointed to a statistical anomaly in the armor loss data. "Sir, we're seeing a significant decrease in complete armor penetrations on modified Shermans. Tanks with the supplemental plating are taking hits but remaining combat effective." Patton examined the numbers. Tanks without deflection panels, 68% catastrophic loss rate when engaged by 88 weapons. Tanks with panels, 31% catastrophic loss rate under similar conditions. What's the weight penalty? 300 pounds, negligible impact on mobility or fuel consumption. And this came from where? Ordnance Research. The chief of staff checked his notes. Field Innovation. A welder at Detroit Arsenal, tested at Aberdeen, approved for field installation, now standard retrofit protocol for all M4 variants. Patton was silent for a moment. "A welder?" "Yes, sir, former coal miner actually. And he solved what our engineers couldn't." "Apparently, sir, the geometry is simple, that's why it works." Patton tossed the report on the desk. "Make sure every Sherman in 3rd Army gets those panels. I don't care if we have to weld them on in the middle of a firefight. If it works, use it." "Yes, sir." The order went out that afternoon. By Christmas, 3rd Army's maintenance depots were running 24-hour shifts, installing deflection panels on every available tank before the winter offensive. The modification that had started as an unauthorized experiment in a Detroit factory was now standard equipment for the most aggressive armored force in Europe. And somewhere in France, Thomas Garrett was teaching another maintenance crew how to bend steel at the right angle to save lives. January 7, 1945, Bastogne, Belgium. Staff Sergeant Mike Kozlowski had been commanding the same Sherman for 8 months, long enough to name it Anna Marie after his wife, long enough to know every mechanical quirk, long enough to have watched 3 different crews rotate through when casualties required replacements. His current crew had been with him for 6 weeks. Driver, gunner, loader, bow gunner, all of them good, all of them scared, all of them aware that Shermans burned easily when German guns found them. 2 days ago, maintenance had installed the supplemental armor. 4 angled plates bolted to the frontal hull, adding what the installation crew called geometry protection. Kozlowski had been skeptical. Quarter-inch steel didn't seem like much defense against weapons that could punch through 3 inches of armor plate. But regulations said install it, so they'd installed it. Now his tank was moving through frozen Belgian countryside, part of a relief column pushing toward Bastogne through German defensive positions. Intelligence reported panzer units in the area, which meant 88 guns, which meant his Sherman was outgunned, out-armored, and relying on speed and numbers to survive. The forest opened into a clearing. Kozlowski saw the muzzle flash before he heard the shot, trained reflex from 8 months of combat. Traverse left, enemy armor, 11 o'clock. The 88 round covered 800 yards in under a second. It struck the upper deflection panel at a shallow angle, exactly as designed. The quarter-inch steel couldn't stop the projectile, wasn't meant to, but it forced the round to change trajectory by 19 degrees. The round tumbled, lost rotational stability, and hit the main glacis plate off-axis. Penetration depth, 2 inches, not enough. Inside the tank, Kozlowski felt the impact like a hammer blow, violent, terrifying, but not catastrophic. No penetration, no fire, no screaming. Target acquired, his gunner shouted. Fire! The Sherman's 75 gun spoke. The shot hit the German tank destroyer at 600 yards, a flank hit that disabled the vehicle before it could reload. Kozlowski's tank kept moving. That night at the maintenance depot, a welder examined the damage. The deflection panel was buckled, one mounting bracket sheared off, the main armor scarred but intact. You got lucky, the welder said. Lucky nothing, Kozlowski pointed at the angled panel. That thing saved our lives. Who designed it? The welder shrugged. Some guy in Detroit, don't know his name, but yeah, it works. Kozlowski made sure his crew saw the damage, the way the supplemental armor had taken the hit, the way the geometry had bled off enough energy to keep the main armor from failing. He wanted them to understand that survival wasn't just luck or firepower. Sometimes it was physics. Sometimes it was someone paying attention to how forces distributed. 3 days later, his tank took another hit. Same result. The deflection panel absorbed the initial impact. Geometry disrupted the projectile, main armor held. Anna Marie kept rolling. March 1945, German border. The reports were accumulating at Army Ordnance Headquarters. Sherman tanks equipped with supplemental armor were surviving encounters that should have destroyed them. The modification wasn't perfect. Close-range hits still penetrated, and flank or rear shots remained catastrophic, but frontal engagements were no longer automatic death sentences. Survival rates for crews in modified tanks, 42% higher than unmodified variants under equivalent combat conditions. The German military had noticed too. Intelligence intercepts showed confusion among panzer commanders about why American tanks were suddenly more resistant to 88 fire. Some attributed it to improved armor metallurgy. Others thought it was additional plating. None of them realized it was just geometry, quarter-inch steel positioned at the right angle to disrupt projectile trajectories. By April, the supplemental armor was standard on 70% of Shermans in Europe. Maintenance crews could install a full kit in under 2 hours. The panels were field repairable using basic welding equipment. When damaged, they could be replaced without affecting the main hull. It wasn't elegant, it wasn't sophisticated, but it worked. And in the calculus of armored warfare, working was enough. May 1945, War Department, Washington, D.C. The war in Europe ended on May 8th. By then, the supplemental armor system had been installed on 4,200 Sherman tanks across 3 armies, 5 armored divisions, and dozens of independent tank battalions. The modification that Thomas Garrett had built in a single night had become standard equipment. The statistical analysis came 3 weeks later. Colonel Brennan, head of Army Ordnance Research, presented the findings to a room of Pentagon officials, defense contractors, and senior engineering staff. The numbers were stark. Tanks equipped with supplemental armor experienced a 61% reduction in crew fatalities compared to unmodified variants when engaged by German anti-tank weapons. 61%, thousands of lives. The modification adds negligible weight, requires minimal manufacturing infrastructure, and can be field installed by standard maintenance crews, Brennan said. It represents one of the most cost-effective armor improvements implemented during the war. A Chrysler representative raised his hand. What's the metallurgical composition? Are we using specialized alloy steel? Quarter-inch mild steel, commercial grade. The protection comes from geometry, not material properties. And who developed this? Brennan checked his notes. Initial concept, Thomas Garrett, civilian welder, Detroit Tank Arsenal. Field testing oversight, First Lieutenant Edward Amos, Army Ordnance Corps. Production implementation, Frank Chen, manufacturing supervisor. The official designation is Armor Supplemental M4 Series, developed under expedited field innovation protocols. The Chrysler representative wrote this down. So did representatives from Ford, General Motors, and General Electric, companies that had spent millions developing armor solutions that hadn't worked as well as a coal miner's bent nail geometry. After the meeting, Brennan was approached by a civilian from the War Production Board. This Garrett, is he being recognized? He received a commendation letter and a temporary technical sergeant commission for his training deployment. Standard acknowledgement for civilian contractors who contribute to military innovation. No medal, no public recognition. Brennan shrugged. He's a welder, enlisted equivalent. The system works, but it's not exactly advanced engineering, just practical field modification. The civilian said nothing, but made a note on his clipboard. 3 months later, the War Production Board published its official history of wartime industrial innovation. The supplemental armor system was mentioned in a footnote on page 147, credited to collaborative efforts between Army Ordnance and Detroit manufacturing facilities. Thomas Garrett's name did not appear. June 1945, Detroit. Garrett returned to civilian life the same week Germany surrendered. The temporary commission expired, the training deployment ended, and he was back at Detroit Tank Arsenal doing the same job he'd done before the war, welding seams on vehicle hulls. The production line had slowed. With Europe secured and Japan collapsing under naval blockade and strategic bombing, tank production was being phased down. The workers who'd built 50,000 Shermans were being laid off in batches, the factory floor shrinking week by week. Frank Chen found Garrett during lunch break carrying a folder. Thought you'd want to see this. It was the Army's final statistical report on armor modifications. Survival rates, penetration analysis, cost-benefit assessment. The supplemental armor system was rated highly effective and recommended for incorporation into future tank designs. Garrett read through it, nodding the technical language that described his work without mentioning his name. They're going to use it going forward. Already are. The new M26 Pershing tanks have integrated spaced armor built into the design. Different configuration but same principle. Chen sat down. You changed armor doctrine, Garrett. Every tank from now on will incorporate some version of what you figured out. Good. That's it, just good. Garrett handed back the folder. The panels work, crews survived, that's what mattered. You don't care that nobody knows you invented it. I didn't invent it. I just noticed something that should have been obvious. Garrett took a drink of coffee. Back in Pennsylvania, when a mine support held up under a collapse, nobody asked who designed the support geometry. They just checked that it worked and used the same design in the next tunnel. This is the same thing. Chen studied him. Most men would want credit. Most men didn't spend 20 years underground learning that credit doesn't matter when you're trying not to die. Garrett stood, finishing his coffee. I'm just glad it worked. He walked back to his welding station, put on his mask, and returned to work. The war was ending. The tanks would stop rolling off the line. Eventually, the factory would convert back to civilian production, cars, maybe, or agricultural equipment. But somewhere, in engineering offices and design bureaus, people were incorporating the principle he'd discovered into the next generation of armored vehicles. The bent nail trick would outlive its inventor. That was enough. 1952, Detroit. Thomas Garrett was 61 years old, retired from welding, living in a small house near the old Arsenal facility. The factory had closed in 1946, converted to civilian manufacturing, and most of the wartime workers had scattered to other jobs. Frank Chen had moved to California. Lieutenant Amos, now a major, was teaching engineering at West Point. Garrett spent his days maintaining his house, working in a small machine shop he'd built in his garage, helping neighbors with repairs. Occasionally, someone would mention the war, ask if he'd been involved, and he'd explain that he'd welded tanks in Detroit. Usually, the conversation ended there. In 1953, a military historian researching wartime industrial innovation contacted him. She was writing about field modifications and had found his name in declassified Army ordnance records related to supplemental armor development. They met at a diner near his house. She was young, earnest, methodical in her questions. The records show you developed the initial concept for spaced armor geometry, she said. Can you walk me through how that happened? Garrett told her about the damaged Sherman, the bent nail, the observation that angles could redistribute impact force. He kept it brief, factual, unembellished. She took notes, and you weren't formally trained in engineering. Coal miner, 20 years underground before the war. But you understood the physics. I understood that loads distribute differently depending on geometry. Didn't need formal training to see that. She published her paper 6 months later. It was well-researched, thoroughly documented, and included 2 paragraphs about Garrett's contribution. The paper appeared in a military history journal with limited circulation, was cited by 3 other researchers, and eventually disappeared into the archives. Most people who read it never noticed his name. 1967, Army Armor School, Fort Knox, Kentucky. Captain James Warren taught armor tactics to new tank officers. Part of the curriculum covered the evolution of tank protection systems, including the development of spaced armor during World War II. The textbook Warren used credited the innovation to collaborative research between Army ordnance and defense industry engineers in 1944. There was no mention of individual inventors, no footnotes about field innovations or civilian contractors. Warren, who prided himself on thorough research, had found references to a welder named Garrett in old ordnance reports, but the information was fragmentary and unofficial. Without corroboration from multiple sources, he couldn't include it in lectures. So he taught the doctrine without the story. His students learned that spaced armor worked because geometry disrupted projectile trajectories, but they didn't learn that a coal miner had figured this out using a bent nail and practical observation. The principle survived, the person didn't. 1978, Pennsylvania. Thomas Garrett died at age 87, in the same small house where he'd lived for 30 years. The obituary in the local paper mentioned his service as a civilian contractor during World War II, his work at Detroit Tank Arsenal, and his earlier career in coal mining. It did not mention that he changed armor doctrine. It did not mention that thousands of tank crew members had survived combat because of his innovation. It did not mention the supplemental armor system that had been based on his geometry insight. His funeral was attended by 17 people, neighbors, a few distant relatives, a nephew who'd driven from Ohio. No military honor guard, no Veterans Organization representatives, no Army historians. He was buried in a civilian cemetery with a simple headstone, Thomas J. Garrett, 1891-1978. 2003, National Archives, College Park, Maryland. Dr. Jennifer Martinez was researching World War II armor development for her dissertation when she found the Aberdeen Proving Ground test reports from July 1944. The documents described experimental armor configurations tested against captured German weapons, including detailed ballistic analysis and penetration data. One configuration stood out: Field Innovation Proposal, Garrett Design. The test results showed significant improvement in survivability with minimal weight increase. The documentation included technical drawings, installation specifications, and a brief note crediting T. Garrett, civilian contractor, DTA. Martinez cross-referenced the name with personnel records. Thomas Garrett, Detroit Tank Arsenal, 1942-1945. Welder. No formal engineering credentials. Temporary Technical Sergeant Commission, 1944. Commendation for training services. She found the original prototype specifications, handwritten notes describing the geometry, the spacing calculations, the mounting bracket designs. The handwriting was careful, methodical, the notes of someone who understood that precision mattered. Then she found the casualty statistics. Sherman tanks with supplemental armor, 61% reduction in crew fatalities. 61%. Martinez spent 8 months reconstructing the timeline. The damaged tanks in Detroit, the unauthorized prototype, the Aberdeen test, the field deployment, the statistical impact. She documented how a coal miner's practical observation had influenced armor design for decades afterward. Modern composite armor still use spaced layers and angular geometry based on principles Garrett had demonstrated with quarter-inch steel and angle iron. She published her findings in 2005. The paper appeared in the Journal of Military History, was cited by subsequent researchers, and contributed to growing recognition of enlisted and civilian contributions to wartime innovation. But by then, Thomas Garrett had been dead for 27 years. 2015, Army Armor Museum, Fort Benning, Georgia. The exhibit on World War II tank development included a restored M4 Sherman with supplemental armor panels mounted on the frontal hull. The placard explained the concept of spaced armor, the physics of projectile deflection, and the implementation timeline. A small notation at the bottom read, "Initial concept developed by Thomas Garrett, civilian contractor, 1944." Most visitors walked past without reading it. The principle Thomas Garrett discovered with a bent nail is now foundational to modern armor design. Reactive armor, composite armor, slat armor, all use variations of the same concept. Geometry disrupts projectiles more effectively than thickness alone. Modern tank designers study spaced armor configurations without knowing the origin story. Military engineers teach deflection angles without mentioning the coal miner who first calculated them on a factory floor. The innovation survived because it worked. The innovator disappeared because that's what happens to people who solve problems without credentials, without institutional backing, without the machinery of recognition. Thomas Garrett never became famous. His name appears in footnotes, in archived test reports, in dissertation citations that specialists read but the public ignores. He received no medals, no monuments, no popular history books celebrating his contribution. But every modern tank incorporates his insight. Every armor engineer since 1944 has built on the geometry he demonstrated with scrap steel and practical observation. He saw a problem that was killing men. He solved it using knowledge from a completely different field. He proved it worked, taught others to implement it, and then went home and disappeared. That's not tragedy. That's not injustice. That's just how most innovation actually happens. Quietly, practically, by people who care more about solutions than recognition. Somewhere in Pennsylvania, there's a grave with a simple headstone. No mention of armor doctrine, no reference to lives saved, nothing that would tell a visitor why the name matters. But in design bureaus and engineering schools and military archives, the principle remains. The bent nail trick outlived its inventor by decades. And somewhere, in a combat zone none of us can see, a tank crew survives an attack because geometry disrupts a projectile before it can kill them. They don't know Thomas Garrett's name, but they're alive because he paid attention. That's the only legacy that matters.